So in this video, I'm going to be covering the dimensioning of cylindrical sections. So this includes the motor, of course, and the rest of cylindrical section we can have in the sounder rocket. In the chapter 4 of Fleeman, the explanations isn't really clear actually. So I'm gonna do another explanation for you, because if you check, I think it's page 288. It mixes up the sigma for the ultimate strength of a material and sigma as a load, so it can lead to a lot of confusion. So because it's a non-guided sounder rocket, I'm not gonna take into account any maneuver bending moments. So where Fleeman talks about maneuver bending moment, well, I'm not going to add them. Okay. So basically, the forces that a cylindrical section is going to withstand are going to be axial forces, which are axial drag and thrust, and internal pressure in the case that the motor is firing, of course. So we're going to add these up. Okay, the thickness required to withstand the actual forces and the thickness required to withstand the internal pressure. We're going to add them up, and then we're going to compare this thickness that we've just calculated. If this thickness is larger than the thickness, the minimum, or the thickness in which the structure buckles, we'll call it buckling. So if this thickness is larger than the minimum thickness that will cause buckling, we'll just stay with this. And if this thickness is larger, then we're going to have to stay with the minimum thickness due to buckling. In high strength materials, like high strength steel, this thickness is going to be larger than this one here. So so the thickness, the weight and the thickness is going to be driven by buckling, not by internal pressure and axial drag, the axial forces. So which will be the case for aluminium. So steel. Okay, to withstand an internal pressure, we're going to need a thickness of the pressure inside, the maximum pressure we expect to have in the rocket, times the radius of the rocket over, let's put the yield strength of the material. So at this thickness, this is the thickness required to withstand the internal pressure. So what about the actual loads? Well, the thickness required to withstand actual loads is, let's put an A. Okay. And then 2 pi yield strength and the radius. Okay. Alright. Then A is going to be the largest when we have thrust plus the maximum dynamic pressure. Let's put, I used A, but let's call it A prime. This is not the axial force, this is the sum of the axial forces. So yeah, let's put a max. Okay. And this is due to axial forces. Alright, so what we do is we're going to sum these two up and add a factor of safety. So let's put T is equal factor of safety times thickness due to pressure. Let's put max here. Maximum pressure. Thickness to withstand actual loads. Alright. And then, after calculating this, by the way, factor of safety, you can use whatever you feel like using. Normally this is from 1.25, 1.5, or more if you like. Yeah, so it's up to you. And then what we will do is we're going to compare this thickness that we just calculated. If this is larger, then a thickness in which a cylindrical section will buckle. So we calculate the thickness at which a cylindrical section will buckle in the following way. This formula doesn't appear in explicitly in Fleeman. It's just a combination of two formulas, but it's clear. I think it's clearer if I show it to you this way. So it's 2 times the total axial forces over Young modulus, pi, and the thickness we just calculated. So we compare these two, and if this thickness is larger, this is the same thickness, or we'll just stay with the thickness. If not, we're going to have to stay. We're going to have to stay with a larger thickness. The minimum thickness required for buckling. Fleeman also talks about the minimum gauge for manufacturing, which is the minimum thickness required to manufacture, to do some manufacturing processes like drilling, drilling holes. Yeah. So he just suggests around 1.5 millimeters as the minimum. So yeah, unless you, it's strange that these numbers will give you, values around 1.5 millimeters, but just in case, yeah, you can't go really lower than this if you have to machine and drill and everything. And yeah, that's about all. So you'll see that Fleeman presents it in a slightly different way. Feel free to choose the one you prefer. So yeah, in the next video we can talk about the fins.